Blocking and confounding in the 2-key design. First, we define blocking. Blocking is a technique used to extraneous sources of variation. It involves grouping experimental units into homogeneous blocks based on some criteria, such as batches of material, technician, day of the week or time of day, or other environmental factor. So we have here confounding. Confounding is a technique that makes some effects indistinguishable by blocking. It is a systematic process of making some effects distinguishable by blocking. Can be beneficial rather than a liability in some cases. In the context of 2-key replicated designs, where we have n replication per cell and perform a completely randomized design, we randomly assign all 2-key times n experimental units to the 2-key treatment combinations. Alternatively, when we have n replicates, we can use these n replicates as blocks and assign the 2-key treatments to the experimental units within each of the n blocks. If we are going to replicate the experimental anyway, at almost no additional cost, you can block the experiment, doing one replicate first, then the second replicate, and etc., rather than completely randomize the n-time 2-key treatment combination to all the runs. There is always an advantage to blocking when we replicate the treatments. This is true even if we only block using time due to the order of the replicates. In 2-key designs with 2 blocks via confounding, the reason for confounding is that the block arrangement matches the contrast of the sum factorial effect. Confounding makes the effect inestimable. Now that you've been introduced to blocking effect, by now I'm going to explain how you can account for blocking and something known as confounding in the 2-key design. Ideally, you would run all experiments in the 2-key factorial design under homogeneous conditions. The ideal often not possible. Experiments will often by block according to some extraneous factor. Multiple equipment setups, different personnel, different raw materials, temporal condition change, and these are other factors. Block size may be smaller than the number of runs in a complete replicate. In analyzing the result, the block effects will be confounded with certain factor effects. And I'll explain what this means here in a few minutes. Let's go back and revisit our example that I've talked a couple of times. So we have here example. Our example is all about crop production. You are an agricultural scientist investigating productivity of wheat. We have 2 different factors, watering and sunlight. And the response is weight produced per day. So what we are going to do is to collect some data with these 4 different experimental combinations. And here's what we get. So, what if there are 2 different combines that harvest the wheat? So a combine is an aqua tractor that harvests the wheat. So maybe we have an older one up here on the left, and we have a brand new super efficient one down here on the right. In order for you to harvest the wheat on time, you have to half of it harvested by this old one, and half of it harvested by the newer one. There's a couple of different ways that we can split 4 experimental runs into the old combine and the new combine. In other words, how we can block the experiment. So here's one. We could harvest one on the left here with old combine and one on the right with the new combine. This means that the experiment with low water would be harvested by the old combine, and this with higher water would be harvested by the new combine. And you might be thinking that there's already some issues with this setup. Or we could do something similar where we harvest the top 2 experiments with the old one and the bottom with the new one, and the bottom 2 with the new. And finally, we could put the 2 different blocks in the corner of this 2-square design. And it turns out that this is the best arrangement because each block, the old combine and the new combine, has a low and high value of A and a low and a high value of B. Any effects will cancel each other out, at least for determining main effect, which are the most important. So let's look at the main behind this. If we want this arrangement where we put the left 2 of the square in the old combine block and the right 2 in the new combine block, we could compute the contrast. And here, we're defining the term delta. Delta is our blocking effect. Delta is increase in productivity between old combine and the new combine. So even if we harvested wheat from the same exact field that had been grown under the same exact conditions, the new combine would have a delta increase in productivity over the old combine. That's what this blocking factor or delta is. We could compute the contrast here for A and B and the interaction effect. And you notice here that at at least 2 of these and the second 2, and we have a positive delta here which cancels with a negative delta here. And in AB, we have a positive delta that cancels with a negative delta. So for B and AB, the blocking effect cancels out, but we're left with the blocking effect delta affecting the main contrast of A. And this, but because what we've done is what we've confounded the blocking effect delta with the main effect of A. Let's look at the third alternative that we considered, where we put the 2 different blocks on opposite corners of this 2 square design. We can compute the contrast of AB and AB. It turns out for me the first 2 of these, the data cancel. But when we look at the interaction effect AB, this is confounded with the blocking effect. For a 2 square design, it's better to put the confounding of the blocks on the higher order interaction. In other words, AB, then it is to confound the blocks with our main effects A and B. In general, we want to confound the blocking effect with the highest order interaction that we can. And in this case, for a 2 square design, that's AB. So we have here sample example. In order to do this, we can set up our table and we look at the highest order interaction. So that's AB here. For the plus 1 in the AB column, we put that into one of these blocks, and for negative ones in the AB column, we put in the second column. And so this is how we can easily split the design into 2 blocks. Now, this becomes a little bit more complicated when we split into more than 2 blocks. Let's take a look at the 2 cube design. How should we choose which experimental treatments go in each block? Well, it turns out that this design with the blocks and opposite corners of this cube is most efficient design. Let's take a look at some example contrast. The main effect of A would be given by this formula, AB and ABC given by these formulas. If we take a look at this, we see that for the main effect of A, we have 2 positive deltas and the 2 negative deltas. So the blocking effect is not confounded with the main effect for A. If we look at AB, we see that we have 2 opposite and 2 negative for the blocking effect. And so AB is not confounded with blocks. But if we look at ABC, again, what we want to do is confound the blocking effect with highest order interaction. For a 2 cube design that ABC, we see that overall, we have a negative 4 delta. So we've confounded the blocking effect with ABC, which is good. And the main effects and binary effect for this 2 cube design are not confounded by blocks. So that's why we choose to do this design. Because we've confounded ABC with the blocking effect, we don't know if ABC effect that we observe, if we observe an ABC effect, is due to an actual effect or it is from blocking effect. The way that we choose the blocks, we get up our 2 cube table, and then I've already sorted the ABC column, highest to the lowest. I've got the ones on the top and the negative ones on the bottom. And so what we do is we assign to a principal block and the top 4 and the bottom 4 where ABC are all negative. For those ones, we assign those to the secondary block. And again, by doing this, we're confounding the blocking effect with ternary effect. The highest order interaction and all other effects are independent of the blocks.